Welcome to Metaminds Academy. This is a lecture series on matrices. This is the third video in the series. In this video, we are going to learn the concepts of Hermitian matrix, Skew Hermitian matrix, Unitary matrix, and properties of Unitary matrix and problems on Unitary matrix. Let us see what is a Hermitian matrix. Before this, we should know what is the complex matrix. Complex matrix is nothing but a matrix whose entries are all complex numbers. So if you take A equal to matrix Aij, A11, A22 like that, these Aij are nothing but complex numbers. So complex numbers means you can have a real number also, but at least one complex number must be there out of all entries. Then we call it as a complex matrix. And if you take Z equal to A plus IB, right? So what is the complex conjugate? Complex conjugate of A plus IB is denoted by Z bar, which is A minus IB. So what we have to do is we have to replace I by minus I. If Z is A minus IB, then Z bar will be A plus IB. So we have to replace I by minus I. Okay. Then what is a Hermitian matrix? So when do you call a matrix to be Hermitian? If A bar is equal to A bar whole transpose is equal to A bar whole transpose is equal to A, then we say that A is a Hermitian matrix. A is a Hermitian matrix. What do you mean by A bar? Here A equal to A is a matrix. Then what is the complex conjugate of the entire matrix A? What we have to do is we have to take the complex conjugate of each entry of the matrix. So that is how you will get A bar. Then A bar whole transpose, if is it equal to A, then A is called a Hermitian matrix. Okay. Then what is a skew Hermitian matrix? So A equal to Aij is a complex matrix. So when do you say a matrix is skew Hermitian? If A bar whole transpose is it equal to minus A? Right? If yes, then A is called a skew Hermitian matrix. A skew Hermitian matrix. Right? So, and coming to the next concept, it is unitary matrix. If you remember in the previous video, we have discussed symmetric matrix, skew symmetric matrix, and orthogonal matrix. We have discussed these three concepts in the previous video, right? So these are related to real matrices. So for complex numbers, the analogous concept of symmetricity is nothing but Hermitian. Right? The analogous concept of skew symmetric matrix is skew Hermitian. The analogous concept of orthogonal matrix is unitary. So these three concepts, that means for the real matrices, these three concepts are for complex matrices. Right? That is why we take the complex conjugate here. Okay. So if you see the unitary matrix, what is the unitary matrix? When do you call a matrix to be unitary? A equal to Aij is a given matrix, right? If A is called unitary if A bar whole transpose is equal to A inverse. If you remember in the previous video, the orthogonal matrix concept. right? This is analogous to what is the orthogonal matrix? A transpose is equal to A inverse is orthogonal. What is unitary? It is A bar transpose is equal to A inverse. Okay. So A bar, A complex conjugate of A whole transpose is equal to A inverse. Then A is called unitary matrix. So coming to this problem, if you take the matrix A equal to show that A is Hermitian and I into A is skew Hermitian, is skew Hermitian. So how to show? Just using the definition of Hermitian and skew Hermitian. So what do you mean by Hermitian? Hermitian means A bar whole transpose is equal to A. This we need to prove, right? So let us take A bar first. What is A bar? A bar is nothing but the complex conjugate of the matrix A. So for a real number, if you take 2, the complex conjugate of 2 is 2 itself, because 2 plus 0i, the complex conjugate is 2 minus 0i, right? 2 minus 0i means 2 only. So the complex conjugate of a real number is the real number itself. Therefore, 2 for 3 plus 2i, it is 3 minus 2i. Minus 4 is a real number as it is. 3 minus 2i complex conjugate is 3 plus 2i. 5 is a real number. 6i minus 6i. Replace I by minus I. For minus 4 it is minus 4 only. 6i. For 3 it is 3. Okay. Now what we have to do is A bar whole transpose equal to A we need to prove. So you take A bar whole transpose. You consider the transpose of this matrix. It is 2 converting rows into columns. 3 minus 2i minus 4. Second row. 3 plus 2i. 5 minus 6i. Next minus 4. 6i. 3. Third row. I am writing third row as a third column here. That is what transposing. So if you observe, this matrix A and this matrix are same, right? This is exactly equal to A. Therefore, A is Hermitian. A is Hermitian matrix. Okay. Now we need to prove that IA is skew Hermitian. So let us write A first again. Multiply this matrix A by I. So I into 2, 2i. This is 3i plus 2i square. 2i square is, I square is minus 1, right? I square is minus 1. So replace I square by minus 1. This becomes 3i plus 2i square is 3i minus 2, right? Because I square is minus 1. So I write it as a plus ib in the form of a plus ib. I write 2 minus 2 plus 3i. Minus 2 plus 3i. Multiply this by I, you will get minus 4i. This is again 3i minus 2i square. It is 2 plus 3i. You multiply and you can check. So 5 into I, it is 5i. 6i square is minus 6. Minus 4i. Minus 6i square is 6. And 3i. So this is the matrix IA. Right? Let us name it as B. You name it as B. Then what we need to do is, we have to show B is Skew Hermitian. What do you mean by Skew Hermitian? B bar whole transpose must be equal to minus B. So right, that is how we can prove it is Skew Hermitian. Now let us consider B bar. Find out B bar first. What is B bar? Taking the conjugate of each and every element in B, replacing I by minus I, we get minus 2I, minus 2 minus 3I, 4I, 2 minus 3I, minus 5I, minus 6, 4I. We are replacing I by minus I. 6 minus 3I. So this is complex conjugate of B. Then let us take the transpose of B bar. What is the transpose of B bar? Write the rows into columns. Minus 2I, minus 2 minus 3I, come here, minus 2 minus 3I, 4I. Second row, 2 minus 3I, minus 5I, 6. Third row, sorry, minus 6. So the second row will come here, okay? And third row, 4I, 6, and minus 3I. Right, this is B bar whole transpose. Now let us take negative sign common from this matrix. This you will get 2I minus comes out, right? The here minus comes out, it becomes minus 2 plus 3I. Minus 2 plus 3I minus 4I, 2 plus 3I, 5I, minus 6, minus 4I, 6, 3I. So if you observe, this is exactly equal to minus B. See, this is the matrix B, and it is exactly 2I minus 2 plus 3I minus 4I, 2I plus 3I, 5I minus 6, minus 4I, 6, 3I. Right? So this is matrix B along with negative sign. This is minus B. So therefore, B bar whole transpose is minus B, means B is skew Hermitian matrix. It is a skew Hermitian matrix. Okay. Okay. Now let us see the properties of Hermitian, skew Hermitian, and unitary matrices. Okay. So coming to the first one, the first property of Hermitian matrix, the principal diagonal of Hermitian matrix must be all real numbers. If you observe, let us go back. This is, if you see in this problem, right? We have proved that just now A is a Hermitian matrix. So what is the principal diagonal of A? The principal diagonal numbers must be all real numbers. Okay. The principal diagonal elements must be real numbers. Real numbers for a Hermitian matrix. Hermitian matrix. So when it comes to this Skew Hermitian, matrix, the principal diagonal elements, all the principal diagonal elements of a Skew Hermitian matrix must be either purely imaginary or zeros. Okay, purely imaginary or zeros. Right. So if you see in this problem, we have taken B as this matrix and proved that B is a skew Hermitian, right? So what about B? What are the principal diagonal elements of B? 2i, 5i, 3i. They are purely imaginary. What is the difference between purely imaginary and a complex number? A plus IB is a complex number. IB is purely imaginary number. Purely imaginary means there is no real part. This is called complex part, imaginary part. This is called real part. There is no real part here, right? It is missing. Therefore, IB in the form of a number IB is called a purely imaginary. 2i minus 2i, all these are purely imaginary. Therefore, the principal diagonal elements of a skew Hermitian matrix must be either zeros or purely imaginary. You can have zeros also there. Next, coming to unitary matrix. So, just now we have seen in the first slide, what is the unitary matrix? Unitary matrix means A bar whole transpose is A inverse, right? So there are some properties of unitary matrices. The first one is if A comma B are unitary, then A into B, the product of two unitary matrices, is also unitary, right? This is first property. The second one is A is unitary, implies A inverse is also unitary. A is unitary means then A inverse is also unitary matrix. And third one, A is unitary. These are all properties. A is unitary implies A transpose is also unitary. A transpose is also unitary matrix. Okay. Let us see whether this matrix is unitary or not. So this is a 2 by 2 matrix. Okay. It's a 2 by 2 matrix. Show that A is unitary. A is unitary matrix. So what we have to do is we need to show that A bar whole transpose is equal to A inverse. That means LHS is equal to RHS. Now let us find out the LHS. What is LHS? A bar whole transpose. So first of all, transpose, keep the transpose as it is. Now let us write the A bar inside. Okay. What is the conjugate of A? It is replace I by minus I. So this is minus I by 2. There is no I here. It's real number only. Root 3 by 2, root 3 by 2 and minus I by 2. Okay. So for this we need to take the transpose. The transpose of this matrix is minus I by 2, root 3 by 2, root 3 by 2 and minus I by 2. You got the same, right? Because it is symmetric matrix. What is RHS? A inverse. So what is A inverse? 1 by AD minus BC into adjoint A by dt. Adjoint A is here D minus B minus C A. Am I right? So 1 by AD minus BC. What is AD? Here in the matrix A, AD means that this into this. I by 2 into I by 2, I square by 4 minus root 3 by 2 whole square. Right? I by 2 whole square minus root 3 by 2 whole square. D minus B. What is D? D is I by 2 minus B minus C A. A is I by 2 again. Right? Now this is equal to 1 by, what is I square is minus 1. Minus 1 by 4 minus 3 by 4. Okay. It is root 3 whole square is 3, 2 square is 4 into I by 2 minus root 3 by 2 minus root 3 by 2 I by 2. So this one is minus 1 by 4 minus 3 by 4 is minus 1. So 1 by minus 1 is minus 1. So you need to multiply it by minus 1. It is minus I by 2 root 3 by 2 root 3 by 2 minus I by 2. Okay. This is exactly equal to this, right? This and this and this are same. So this is equal to LHS. So LHS is equal to RHS. Therefore, A bar whole transpose is A inverse. Hence, A is unitary. A is a unitary matrix. So that is how you can show a matrix is a unitary matrix. Okay. So that is the end of video 3 on matrices. If you have not subscribed yet, please subscribe to my channel. Please like the video if you really like it. Share it with your friends. And please give your feedback or impressions or suggestions in the form of comments. Thank you so much. Meet you in the next video.